video, I had discussed about uniform continuity and some concept about this continuity with some example. And today I will discuss the properties of this uniform continuity elaborately. At first I will say the Lipschitz continuous function, because if a function is Lipschitz continuous, then the function always will be uniform continuous. And the definition of Lipschitz continuous function is a function f from I to R over the set I, where I be the subset of R, is called Lipschitz continuous if there exists a constant capital L where L greater than equal to 0, such that absolute value of fx and f of y less than equal to capital L times absolute value of x minus y, where for all x and y belongs to the interval I. That means the difference of output is bounded by L times difference of input. Okay? Where we call this capital L is the Lipschitz constant of the function f over the interval I. Equivalently, f is Lipschitz continuous if there exists capital L such that from this line we can tell easily absolute value of fx minus f of y divided by absolute value of x minus y, which is always less than equal to L for all xy belongs to I. And this is actually the slope of the line x fx to y fy, and which is bounded by L. This is the geometrical meaning. This is the graph of f, and this is the slope of the function, which is defined as L. Here notice, this is the function, main function is contained between this slope. Are you getting geometrical meaning of this inequality? Absolute value of fx minus fy strictly less than equal to L times x minus y. Okay. I have actually defined before part only for R. But when the function will be multivariable calculus, consider f from Rn to Rm is called locally Lipschitz at the point x0 where x0 belongs to Rn. If there exists a ball b of x0 comma epsilon with epsilon greater than 0 and capital L greater than 0 such that distance between f of x1 minus f of x2 less than equal to distance between x1 L times x1 minus x2. Here the distance has defined as norm, and here notice for all x1 x2 belongs to b of x0 epsilon, and we all of us know b of x0 epsilon in multivariate calculus means this is the set of all point x in Rn such that norm of x minus x0 less than epsilon. That means this is actually the open ball around x0 of radius epsilon. That means b of x0 comma epsilon lies subset of Rn, and here for this inequality this x1 and x2 lies in this ball. And if these inequalities satisfy for multivariable calculus, then L is called Lipschitz constant and the function is called locally Lipschitz continuous function. In general, L may be different. Actually, L depends on the point x naught and epsilon. Okay? Well, now I will prove if a function is given Lipschitz, then f is always uniform continuous on the domain I. Here given the function f from I to R, that means given epsilon greater than 0 and we want a delta greater than 0 such that for all xy be the member of the domain I with the condition absolute value of x minus y less than delta imply absolute value of fx minus f of y less than epsilon. And I will usually start from here and after back calculation I will find the value of delta. Since here given the function is Lipschitz continuous, so difference of the output fx minus fy will be less than L minus difference of the input, where L greater than 0. So from this line consider absolute value of x minus y strictly less than epsilon over L. Then let's come back our original proof. And the proof is given epsilon greater than 0, choose delta equal to epsilon over L, where L is fixed number. So when absolute value of x minus y less than delta, since the function is Lipschitz, so difference of the output fx minus fy less than L times difference of the input. And since absolute value of x minus y less than delta, that means this is less than delta, and I have chosen delta equal to epsilon over L. So this is less than L times epsilon over L, which is always less than epsilon for all xy belongs to I. So our proof has done. Since absolute value of f of x minus f of y less than epsilon for all xy belongs to I, so any function which is Lipschitz continuous always will be uniform continuous. Okay? And uniform continuous function always does not imply Lipschitz continuous function. Let's see one example. Consider a function f from close interval 0,1 to 0,1 such that x maps to square root of x. We all of us know square root of x in the domain close interval 0,1 always uniformly continuous, because here the domain is closed and bounded set and the function is also continuous function. So this function always uniformly continuous function. Now let's verify. Is this function is ellipsis continuous? For ellipsis continuous, we all of us know we have to prove absolute value of square root of x minus square root of y. Here absolute value less than equal to k times absolute value of x minus 1. Where for all xy belongs to close interval 0, 1. We have to prove for ellipsis continuous this. Take the point x equal to 0 and y equal to 1 over 4 k square. Put the value. Notice, after putting root x minus root y equal to 1 over 2k, which is greater than always 1 over 4k, which is equal to k times absolute value of x minus y. So, our condition for ellipsis continuous function has broken here. So, the function is not ellipsis continuous, but the function is uniform continuous. Now, consider a graph. This is the set of all function on A. Now consider this is the set of all continuous function, and since set of all continuous function does not imply always uniform continuous, but uniform continuous always imply continuous. So this is considered set of all uniform continuous function, and this is considered as a ellipsis continuous function. Okay. This is the graph of all function. Well, now I will say one most common example, sin x, which is uniformly continuous on whole real number r. We all of us know the graph of the sin x. Sin x is oscillate between +1 to -1. Okay. Now consider epsilon be any positive number, and for all delta greater than 0, such that x minus y less than delta imply f of x minus f of y equal to sin x minus sin y, and which is equal to 2 sin x plus y over 2 and sin x minus y over 2. We all of us know it, which is less than equal to, we can write 2 sin x plus y over 2 times 2 sin x minus y over 2. And we all of us know modulus of sin is always less than equal to modulus of x, and sin x vary from +1 to -1. So at first use this relation here. So this would be less than equal to 1, and now apply this relation here. So this would be absolute value of x minus y. So I have got absolute value of sin x minus sin y less than equal to absolute value of x minus y. And here Lipschitz condition also has satisfied. Here L equal to 1. So we can tell easily sin x is uniformly continuous on whole R. Okay? Sorry, here y, just printing mistake. Now I will prove the function sin x square is not uniformly continuous or on whole real line. We all of us know the graph of sin x square, and when it's approach to infinity, this oscillation would be faster and faster. This is the graph of sin x square. Here the value oscillate between +1 to -1. At first consider sin x square. Consider x square equal to pi over 2 plus 2n pi. That means x equal to square root of pi over 2 plus 2n pi. And at this point, we all of us know the value of sin x square is 1. Now consider other point, in which point the value of sin x square is -1. Consider this point, x square equal to 3 pi over 2 plus 2n pi. Then x equal to square root of 3 pi over 2 plus 2n pi, and at this point the value of sin x square equal to -1. Okay. Now consider epsilon equal to 1, and notice here 1 point square root of pi over 2 plus 2n minus 2n plus other point. Consider other point is y. That means absolute value of y minus x. So here would be also y square. Square root of 3 pi over 2 plus 2n pi minus square root of pi over 2 plus 2n pi. Now after calculating, this would be 3 pi over 2 plus 2n pi minus square root of pi over 2 plus 2n pi times square root of 3 pi over 2 plus 2n pi plus square root of pi over 2 plus 2n pi divided by square root of 3 pi over 2 plus 2n pi plus square root of pi over 2 plus 2n pi. And after calculating, this value would be pi over square root of 3 pi over 2 plus 2n pi plus square root of pi over 2 plus 2n pi. And we all of us know as n tends to infinity, this value, this difference must be absolute value of y minus x. This difference must be tends to 0. So, for epsilon equal to 1, I have got y minus distance between y minus x less than delta. But for this point, the distance between y minus fx would be 2, and here I have chosen the value of epsilon equal to 1. That means this difference always greater than epsilon. So our given function sin x square is not uniform continuous on whole R. Are you getting? Well, there exists a nice theorem. Consider a set A which is non-empty and compact in R. We all of us know compact in R means closed and bounded set. And if F be a mapping from capital A to R which is continuous, since the set is domain is closed and bounded and the function is continuous, so F must be uniform continuous. We all of us know it. Consider a non-empty set B which is subset of A. Now consider a continuous function Z from B to R. Actually, G equal to F which is restriction of capital A, the set capital A. Since the function f is uniform continuous, if the function g is continuous, then we can tell easily g is also uniform continuous on the set R. Now consider a nice example. F be a mapping from open interval 0, 1 to R, and the function is look like fx equal to x sin 1 over x. And this function is always continuous function because the mapping is look like x maps to 1 over x, and if we apply sin, then this would be sin 1 over x. Since both functions are continuous, so their composition must be a continuous function. So our given function is always continuous. We all of us know it. Also, the graph of the function is look like, I have draw it in my earlier video, x sin 1 over x, and at the point 1, f of 1 equal to the value 1 sin 1, and limit x tends to 0, x sin 1 over x equal to, since limit x tends to 0, x equal to 0, and sin 1 over x is a bounded function, so this limiting value is 0. Also the function f of 0 equal to 0, and since the function f is continuous on the closed interval 0, 1, so I have defined a new function g from closed interval 0, 1 to R, where f is a restriction on the function g on the closed interval 0, 1. Okay. And since g is a continuous function on the closed interval 0, 1, closed and bounded interval, this is, so g must be uniform continuous. And since the function g is uniform continuous, so our restriction function f must be uniform continuous on the set open interval 0, 1. So our given function is uniform continuous on open interval 0, 1. Are you getting this theorem? This is very important theorem. Oh. Now, I will discuss one question of CSR Net. The question is, which of the following function is or are uniform continuous on the open interval 0, 1? There exist rules by the restriction theorem. If a function fx is defined on the set open interval ab, if the function is continuous and limit extends to a, fx exists finitely and limit extends to b, fx also exists finitely, then our given function fx must be uniform continuous on the interval AB. Are you getting these rules? Okay. That means if the limit exists at the end point of the interval and if the given function is continuous, then this function must be uniform continuous. And here notice, here open interval 0, 1, we all of us know limit extends to 0, 1 over x equal to infinity. So since this limit cannot be finite at the point 0, so function fx equal to 1 over x cannot be uniform continuous on the interval 0, 1. So this is wrong option. Second option is sine 1 over x. Okay. This is also oscillatory function, and we all of us know limit extends to 0, sine 1 over x does not exist. So option 2 also wrong option. And option 3 I have proved few minutes ago, this is always true because limit exists at the end point to end point, and we all of us know the fourth option sine x over x, we all of us know this limit always exists at the point 0 and at the point 1 also. So our right option is 3 and 4. Are you getting the method? This method is very important for any competitive exam. This is just shortcut trick. Okay? Well.